Good evening. This is our 666th programme. 666, the devil's number. So we're going to talk about things we don't understand. I don't mean the Wishing Worm Nebula or the Ghost of Jupiter. Things we really don't understand. They beat us. They're so deep. Well, will we ever understand them? Or is there some reason why we can't? Something's stopping us. With me, three experts, Dr. Kate Land, Professor Gerry Gilmore, and Dr. Chris Lintop. And I'm going to be devil's advocate, so let me give to you, Gerry. Now, in our cosmology, everything begins with a Big Bang, 13.7 thousand million years ago, all based on that, but supposing there wasn't a Big Bang, what then?
You're right. All of modern cosmology is based on the idea that we know there was a beginning. Now, that's based on three pillars, three foundations. The first is that the universe was denser, was hotter, was smaller long ago. The universe is expanding now. Long ago it was smaller. Secondly, it's based on the fact that we can see the leftover heat from that origin, and that's what we call the cosmic microwave background.
How?
Well, it's television frequencies, actually. It's the static on your TV in the pre-digital days. So this room is full of the microwave background. The entire universe is shining with this stuff, and it's just television noise. And so we can map it to very high precision. And the third pivot of the Big Bang is the ash from the Big Bang, which is the elements of which we are made, the hydrogen, the helium, and the little tiny trace of lithium that was left over from the Big Bang. So we can measure the temperature of the Big Bang from its radiation, the microwave background. We can measure its age from the rate at which the universe is expanding now, and we can measure the ash that came from it from the light elements. So the fact that there was some sort of hot, dense event 13.7 billion years ago is, I think, pretty well established. We don't know anything at all about what there might have been before it, and we're not completely sure we've got the correct description of it, and we don't have much of an idea at all about what's going to happen a long time after it.
Was there before?
I don't think we have a good understanding of what happened. We just like to say that time was created as well at the Big Bang. So at the moment, I don't think we actually have a framework in which we can even ask a question as to what happened before the Big Bang. There are some models which don't really have a beginning, where the universe is actually cyclic and it's got an infinite past. But I think the more conventional model is that time began at the Big Bang.
What do you think of that, Tristan?
Well, we can make sensible comments back to a tiny fraction of a second just after the beginning. But it's true that our theories break down at the beginning. So to say anything sensible about the Big Bang...
So we just don't know.
We just don't know, that's correct. But let's look at what we do know. I mean, what convinces me that the Big Bang is correct is that we look back far enough that we see that the universe was different in the past. We see smaller galaxies, on average. We see them filled with younger stars. And we see the building blocks of the universe that we come to know today. And the furthest we can see is what Joey's already been talking about, which is the microwave background. And Kate, this is your territory. Why do we see this glow from the Big Bang at all?
It is effectively the hiss left after the Big Bang explosion. You're seeing the radiation left. Yeah, the universe wasn't always transparent. There was a time when the universe was hot and dense enough that photons, so that's light particles, couldn't travel freely through the universe. They've been constantly scattered off free particles. And it wasn't until the universe cooled to about 3,000 Kelvin that it became transparent. It's like looking at a cloud on a cloudy day. You can't see inside the cloud, you can only see the edge of the cloud. And that's what we have as well. So we get to look back in time the furthest we go, but we actually get to a point where the universe was opaque. And so we can't see earlier than about 300,000 years.
Can it be that our time scales are completely wrong?
Possible. Anything's always possible. But being 300,000 years fits with lots of other observations. We know it was 3,000 Kelvin then, and we know it's 3 Kelvin now. So we know that space has expanded about 1,000 times since. And so that kind of, if we think we know the age of the universe, then it kind of limits what time the radiation was given off.
We should say we're talking about space expanding, but we should talk about the evidence for that. So, Gerry, why do we think that space is expanding at all?
Now it's just the good old Hubble redshift. So now we look away and we see that everything is expanding in every direction as we look away from us. Now that's a really well-established phenomenon.
Expanding into what?
That is a much more interesting question. And there's one other fundamental observation of the universe that is so fundamental we all forget about it. And the interesting thing there is that time is only going in one direction. You won't have noticed this, Patrick, but you're actually getting older.
I know it.
And we're all getting older, and it's a really fundamentally interesting question. Why does time only go in one direction? It's not supposed to happen like that in basic physics. Time is supposed to be symmetric. But the fact that time only goes in one direction is one of the fundamental pieces of information about the universe that tells us that the past is not the same as the future. And so this expansion of the universe actually is segregating a history which is different from the future. And there are probably some really fundamental connections between why time does that and what the universe is really made of.
How did the Big Bang happen?
Yes.
This is the whole point.
We've conceded that one to you.
Well, I know, but I say I'm being devil's advocate here. And is there something stopping us finding out?
Well, that is a very interesting question, Patrick, and it raises two issues. The first is, do we have a fair census of what the universe is made of? And the answer there is changing very fast. In fact, I remember answering this exact question to you 10 years ago and giving you a very different answer than I'm giving you today.
I do indeed, yes.
But as well as the question of do we have a fair census, and this raises the issues of dark matter and dark energy and things that we'll come to in a moment, it also raises the question of whether or not the universe is simple enough for us actually to understand, and whether or not the bit of it we live in is actually a fair sample of what's really out there, or whether there's stuff that's simply beyond our horizons forever. And if that is the case, then that is the limits of science. You know, we simply can't do science as we define science today on things that we can never know. But of course we're all optimists as well as being little devils, and so we proceed to try and do the best we can with the limits we have. And frankly, that raises quite enough intellectual challenges without worrying too much about beyond the horizons.
Well, we can see the effects of dark matter because they have gravitational effects, and these seem pretty definite. But what is dark matter? If you say something we can't understand, well, another fudge, isn't it?
Well, we can see the stars in the galaxy. We can see how the stars are rotating in the galaxy. If we add up all that mass, it actually turns out that those galaxies should really be falling apart. The galaxy rotation curves, we call them, the stars are moving a bit too fast for the matter that we see inside the galaxy. And so we've had to invoke this dark matter. So you can call it a fudge, but it turns out that it's incredibly consistent with all our observations. Oh, yes. Having this simple, transparent particle that weakly interacts, but has a mass, just doesn't interact with light. Having them in galaxies works very well with other observations because we need them in galaxy clusters, we need them in the early universe, we need dark matter in everything we look at.
And how much of it is there? That's the next question.
Quite.
Gerry.
Well, a lot.
Yes,
yeah,
there is a lot. Yes, no, you're right. I mean, when we look at the universe, we essentially see a size 0 universe. But when we weigh the universe, we see a size 6 universe. And there really is 5 or 6 times more weight in the universe than there is light. But it's not shining, this stuff. So it's called dark matter. Now, it's not dark at all. It's actually transparent matter. And we're lucky that it isn't dark, because if it was dark, it would block our view, and we wouldn't be able to see very far, and we wouldn't be able to do very interesting astronomy. Fortunately, it's not dark, it's transparent. That tells us an awful lot, just that simple statement that it's transparent. It tells us that it's not made of the same stuff you and I are made of. Because the stuff you and I are made of, hydrogen and helium and so on, knows about electromagnetism. Good old Maxwell.
So it interacts with light, therefore.
So it creates light and it absorbs light and it interacts with light, and so we shine. That's why we shine. We shine because we're made of electricity. Whereas most of the universe isn't. Most of the universe knows about Newton, and it knows about Einstein, and knows about gravity, but it doesn't know anything about Maxwell.
Are there any other ways we can explain these various phenomena without introducing something we can't understand, can't see, and can only postulate? Is there anything else to do to get rid of dark matter?
There is another idea. So the only way we know the dark matter is there is by its gravity.
Yes, exactly.
We see it bending light when it under gravitational lensing events. We see it helping the orbits of the stars in the galaxy. But what if perhaps our theories of gravity are wrong?
Exactly.
So we've inferred dark matter just by its gravitational interaction.
Exactly, my whole point.
And it's interesting to think that we had Newton and we had his theories of how gravity worked, and it worked very well. It worked perfectly for the Earth, quite well for the solar system. Not perfectly, did it, you know?
No, well, Mercury was wrong, but you
Good
can do
enough.
the rest of the
Good
planets.
enough. And then a couple of centuries later, Einstein came along and worked out that actually, on bigger scales, it does need to be modified. And he had tweaked Newton's model and came up with general relativity. And what's to say, in another century, we're going to have to tweak it again. Extrapolation from a law of gravity that works on the Earth to the solar system and then to galaxies and then to the whole of the universe. I think it'd be quite naive to think that actually you could apply laws so far to the whole universe.
We also have another option, because modifying gravity turns out to be hard,
It
right?
does.
Especially getting it to fit with all of these observations. So let's do what astronomers always do. Let's blame the particle physicists. So, Gerry, is there any hope that they might provide a set of weakly interacting particles that we can use for our dark matter?
We now realise that actually there are lots of things that we don't really understand about the universe and about the nature of matter. Why is the universe made of matter and no antimatter? It shouldn't. It should be perfect. But there's more ordinary matter than there is antimatter, and we don't know why. And in fact, there are about 13 of these little problems that you can think of. And historically, every time you get a problem like that, it's led to the explanation has led to the discovery of a new type of particle. For electromagnetism, we have photons, we have light, and so on, and all the other forces all have their own particles associated with them. We know that there must be a lot more types of particles. The most popularly discussed these days, of course, is Peter Higgs's Higgs boson that we hopefully will see in a year or two.
Well, we see the various phenomena. We invent particles, still more particles, none of which you can see, none of which you can understand. Even so, with all that, it still doesn't explain all the mess.
Yes, well, here we enter the realm of dark energy.
Exactly.
Dark energy is a label. You're right, precisely right, Patrick. We don't have a clue what it is. Absolutely no idea at all. It shouldn't exist. There shouldn't be the amount of it that there seems to be. Everything there was completely wrong. And that's telling us that nature is cleverer than we astronomers are, and nature keeps surprising us, and that's great, that's exciting. But as far as dark energy is concerned, the observation is really very simple. The universe should be slowing down. There was a Big Bang, as we discussed, and there is weight in the universe, you and me. And we are pulling against the universe and slowing it down, the same as a rocket goes off into space and the weight of the Earth pulls back. So the whole thing should be slowing down. In fact, the universe is not slowing down, the universe is accelerating. And it seems to be accelerating in this perfectly uniform way. It's expanding faster and faster and faster.
Why?
That is an interesting question. What this seems to be is just some property of space-time itself, which drive just empty space-time, nothing to do with its contents, nothing to do with the matter, but space-time itself seems to have, as its very nature, it seems to want to expand and make itself more of a vacuum.
So once again, we're introducing a new concept which you don't understand and can't see.
And which accounts for 70% of the energy in the universe.
But it fits the observations. But it comes from two observations, doesn't it? One is that the universe, the expansion is accelerating, but also because we don't see enough mass to make up the whole cosmic pie.
One of the most fundamental things we know about the total amount of stuff there is in the universe, Patrick, is that we can actually weigh the total amount of energy. We can count all the energy in the universe. We can weigh the weight and we can count whatever else there is as well. And we do that in an incredibly simple way, and it's just basic school geometry. See, when I draw a triangle on this table in front of me, I know that the angles of that triangle will add up to exactly 180 degrees. That's stuff that Euclid discovered long ago and we know is correct. If I do the same thing on the surface of the Earth, well, the Earth is curved. And so the angles of that triangle will add up to more than 180 degrees. And so by measuring, quite simply, the angles in a triangle, I can tell whether the surface I'm on is curved or whether it's flat. And it could be, the number could be less than 180 degrees if we were shaped like a saddle. And so I can measure those angles from the cosmic microwave background largely, and I can measure the angles of the universe, and I can tell very accurately what shape is space-time itself. And that corresponds to how much stuff there is in the universe. And so we know actually very accurately from basic geometry, measuring angles, that the universe contains just a little bit under 6 hydrogen atoms per cubic metre. But you say, well, that's the equivalent weight. What is that weight made of? Well, all our ordinary matter and our dark matter only makes up about a quarter of it. So clearly, once again, we've weighed the universe and we've said, hey, there's something else as well as ordinary weight there.
Yeah, that's the thing same with the dark matter. We've got these horrible fudges we've had to put in.
Exactly.
But they fit with a number of independent observations. And so I think a lot of people like to think maybe we're just making this up as we go along. But while it keeps being consistent with everything, it's quite hard actually to find out much about it.
Can we get rid of it?
We have to assume that, well, actually, our patch, everything we can see, is a good representation of the universe. So there might be a lot more universe beyond what we can see. We like to think that our patch is big enough that it's kind of a good average. And that, by making that assumption, it allows us to apply general relativity and we can infer dark energy. But what if our patch was actually quite odd and it wasn't representative? So that's quite a worrying thought. But that's a possibility that maybe just locally we have an acceleration and really the whole universe doesn't have dark energy in it.
That's about the 10th assumption so far. You know, looking further ahead, you say it began 30.7 million a year, the Big Bang. Well, I wonder. Even so, how is it going to end? We're in at a big crunch or a big squash or what?
We realise that the universe is actually, we don't realise, we assert that the universe is going to live forever. So the universe had a beginning, but it has no end.
It's speeding up, after all.
It's even speeding up. It's going to accelerate into nothingness rather soon. And that is bizarre in the extreme. I think even those of my colleagues who like most cosmologists, are always confident but often wrong, find that puzzling. Why is it then we end up saying that we are alive now at basically the only fraction, the only instant in the history of the universe when you could actually do astronomy? Because for almost the entire future of the universe is going to be so dilute you won't be able to see any stars. There'll be just a few little atoms on your own.
And yet here we are.
And yet here we are. Now that makes us so unlikely that people react in two ways. One said, well, that's the way nature is, we just won the lottery ticket. You can't win a lottery ticket, of course, unless you have a lot of losing tickets, and so all those other universes out there are empty, and that's probably the most common way cosmologists react to that today. Everybody else says, that is so absurd. I suspect there's some really big piece of the jigsaw that we haven't spotted yet.
I wonder, some underlying fundamental problem that's hidden from us that could undermine all these theories. In other words, can we be completely wrong now? There's something behind it. If so, can we find out, or are we being stopped from finding out? 666.
Well, all we can do in these circumstances is make as many observations as we can. And the largest observation we can make is the microwave background.
The earliest as well.
So what do we learn from looking at the microwave background? What does it tell us about the early universe?
Well, it tells us, obviously, about the period before. So we said it's at 300,000 years, but we think that something happened in the first 10 to the minus 33 seconds that has left imprints on the microwave background. So it's our best probe of the very, very early universe. But also, as I mentioned, trying to figure out if our patch is weird. It's a good thing to use for that because it is the largest observation. And what we actually find is that the cosmic microwave background radiation is incredibly smooth. To 100,000, 1 part in 100,000, it is completely smooth from one part of the sky to the other. It's smoother than a white piece of paper. And that really, really constrains this idea that, well, maybe we're just in an odd piece of the universe. When the microwave background was first detected in the 1960s by Penzias and Wilson, it was actually very, very smooth. But since then, in the 80s, we've been able to see the fluctuations. And that's key. If there weren't any fluctuations in it, we wouldn't be here, because those are the seeds. The fact that there are little overdense patches and underdense patches, over time, gravity has slowly caused them to collapse, and that's why we get the structure around us.
I can't think of any other problems with the same note.
I think there are 3 problems left. And there's a solution that solves all 3, but it's not a nice solution. So the problems are, as Kate said, the microwave background tells us that the early universe was very smooth. Why should it be that smooth? We know that the universe, as Gerry said, is flat. There's just the right amount of matter. Why should we be there? And also, we need these small fluctuations in the microwave background to produce galaxies so that there can be astronomers and there can be the sky at night. But why were the fluctuations there at all? So, Kate, how do we resolve these 3 problems?
Well, it's interesting. We kind of consolidate these 3 debts into one in some ways by having this, what we call inflation. So we think, and it's a very simple idea, but we think the very, very, very early universe. And traditionally we even say this is before the Big Bang. That's how cosmologists tend to talk about it. Is in the first 10 to the minus 34 seconds, there was a period of rapid expansion where space expanded faster than the speed of light.
Why?
Well, it explains all these three problems.
But when it happened?
We don't know how it happened.
Exactly.
That's why, I mean, it's just kind of like shifting three debts into one.
Exactly.
Because this one simple idea explains all three things. It makes your little patch of the universe expand very quickly. And so, like if you were standing on a football, you'd see that the football was round. And if that football rapidly expanded, you could very quickly think it was flat, like standing on the Earth.
And no measurement you could make would tell you anything otherwise.
No, and so it means whatever the initial conditions were, if there was a period of rapid expansion, you'd always end up with a patch of the universe that looked flat. It also makes everything very smooth. So at the moment, well, without inflation, we don't understand why one side of the sky is the same temperature as the other. They should never have been able to communicate. Radiation and heat should never have been able to transfer.
So they should never have reached equilibrium,
But they're
essentially.
such perfect temperature. They're exactly the same temperature almost. And inflation does exactly the same thing. You have a small patch where radiation was able to transfer, and then the rapid expansion meant that these parts, which were in causal contact, that's what we call it.
They could talk to each other.
They could talk to each other, basically, were pushed apart. But the amazing thing about this simple idea of inflation, makes the universe smooth, but it also gives it these little seeds, these little fluctuations. And so we think that quantum fluctuations in the vacuum were expanded rapidly, and so they went from scales that we can't even see to what we call classical scales, those scales which are relevant to you and
So
I.
the seeds that form the galaxies after inflation before were tiny fluctuations on scales smaller than an atomic nucleus.
That's what we think. So it's kind of a wacky idea, but it works.
It works very nicely. But, as you say, it is an idea. But space expanding faster than light, I find that very hard to see.
You might think it goes against the fundamental kind of thing that we have in general relativity, that nothing can travel faster than the speed of light. But that's that nothing can travel through space faster than the speed of light. Space itself, it can pretty much do what it likes, and it doesn't break any of our laws at the moment to have space rapidly expanding faster than the speed of light. There are galaxies out there that look like they're moving away from us faster than the speed of light.
We can try to test inflation. Have we found any problems already?
Well, generally it's very consistent with our observations of the cosmic microwave background, but there are some problems. And so the cosmic microwave background has these hot and cold spots, these quite random ripples. But on the largest scales, these patterns should be quite random over the sky. They shouldn't form any particular
if you blur
structure.
these small patterns into larger pixels, you shouldn't see any pattern at all.
Not particularly. You should just be quite random. And what we actually see at the moment with our current observations of the cosmic microwave background is that, yeah, when you blur to big pixels, you seem to get this pattern. You seem to get the hot and cold spots all aligning. And they seem to be marking out a preferred direction, which has been called the axis of evil. You'll like that for this programme. So there seems to be this axis of evil in the cosmic microwave background, which inflation predicts it shouldn't be there. Inflation, because of this rapid expansion, really averages everything out, and there shouldn't be an up or a down. The universe shouldn't have a left or a right.
Yes, as you say, I'm bound to be rather wary about the axis of evil. What do you think about it, Gerry?
Well, given your current mood, Patrick, I think you'd rub your hands in glee and
Yeah,
dance about the
I
moon.
did rather. 666, I did.
Absolutely. Yeah, it must be said that there's two interesting things about the axis of evil, actually. One point Kate already picked up. The first is it real? And only future measurements will confirm that, yes or no, because it's a very marginal detection. It's right at the limits of what we are able to measure. Fortunately, the European Space Agency is launching this new satellite, Planck, which I'm sure you'll do programs about very soon. So we'll know whether it's real soon. The second thing is that it is this test of whether or not what we can see is really a fair test of what's really out there. And it's possible that we're just a little bit unlucky. Our universe is nearly perfect. It's perfect enough that you and I are here to talk about it, but perhaps it's just a little bit defective. And if so, this would be a hint that the universe is not quite as perfect as our simple explanations would have it. In which
Very
case,
strange if it were.
well, it would be hinting that there are even more complex explanations going to be required than those we've been happily speculating about today.
I know, with all the assumptions and fudges, we got somewhere, but if someone could look back on this, our programme 666, in, shall we say, a couple of 100 years' time, will they say, all this is completely obsolete now? I wonder.
I'm sure they will.
Patrick, I bet if you look back on program 66, you'll be able to say the same yourself now.
I do. I remember I did one program about Venus, and there I made 6 statements about Venus, all of which were backed up by the best evidence, and every one of which turned out to be wrong.
Well, there's a nice historical analogy with this, is that's the famous state of physics in the year 1900. Many, many people summarised the state of science at the time, and famously Lord Kelvin said, physics is becoming coherent, we soon will know everything we need to know, but there is this little cloud on the horizon. He was actually referring to what today we would call a cosmological constant, a zero-point energy.
Quite.
But that cloud cleared away, it became transparent, and it left behind Planck and Rutherford and Einstein. So that tiny little patch, that tiny little uncertainty in physics created atoms. Remember, at 1900 they didn't know about atoms. They didn't know about relativity. It took that whole new science of quantum mechanics and special relativity and general relativity to understand what was behind that little cloud. Now we have 2 or 3 little clouds on the horizon, and there is no reason to assume that what's hiding behind those clouds isn't at least as challenging, as exciting and as imaginative as what was hiding behind our one little cloud.
Would you agree on that one?
Yeah, I think our horizons physically and kind of mentally have expanded a number of times over the last 2,000 years. You know, we used to think the Earth was everything and it was at the centre, and then we realised after a long time that actually the Sun was the centre. And still left just our solar system, and then we realised the other stars were just like our Sun.
Yeah.
We got to our galaxy, and it was only 100 years ago that we actually realised there were other galaxies. And so I'm sure our horizons are going to expand again.
What do you think of that, Tristan?
Well, I'm an optimist, so I think we're going to make progress on this, but you could look at which problems we're going to solve. So I'm confident that we'll get a good handle on dark matter in the next few years. I trust the particle physicists. I think they're going to find some candidates. Dark energy. We don't have any theoretical underlying reason for this acceleration to cause. It's hard to think of observations that would really help, although we're doing our best. So I think that's a much harder problem. We will make progress, and we'll get there eventually.
It's a more recent one as well. It's only really been back for the last decade, so we've got more. I think we should give ourselves a bit of a break that we don't understand it completely.
The whole of science is based on the truly astonishing experiment, which we really don't understand. Even more fundamental thing we don't understand, anything we've talked about, is that our brains are actually capable of understanding the universe. Now, perhaps there's a limit. I don't know.
Quite. We've come to various brick walls and we've surmounted them. We've got several now that we can't see over, not quite sure whether there is an over, and that may be hidden from us. I wonder, are we ever going to solve these things, or is something like 666 going to stop us doing so? We just don't know. Kate, Gerry, Chris, thank you very much. Well, next month, much nearer home, the planet Saturn and the Cassini probe. Until then, from all of us, good night.
All this week, BBC4 presents the category finals of Young Musician of the Year, each night at 8, beginning tonight with Woodwind. The stars of tomorrow, today, next.